Hey guys, Ms. McCorn here. This is Unit 4, 4.9 Redox Reactions Part 2. So this is really just a continuation of what we did in the last video. Okay, so in the last video we left off where we were talking about redox reactions and acidic solutions, but what we did not talk about is any of the nitric acid. We talked about all the strong acids except for nitric acids. So when there is a reaction between a metal and a nitric acid, the nitric acid is going to oxidize those metals. So if it is a very dilute nitric acid, you'll end up with the nitrogen monoxide as a product, but you could actually also end up with the same thing here, but you could end up with nitrogen dioxide as a product as well. So if that is the case, either of these answers would be acceptable. This is if you have a very concentrated solution of nitric acid to start out with. So this is just your balanced chemical reaction if you have a nitric acid in the place of any of those other strong acids. An example of that would be right here, a solid copper penny. Okay, if you see here you have copper reacting with nitrate. This is your balanced equation here. So you have your nitrate ion and then you get nitrogen monoxide and copper. This can only be balanced using the half reaction. So you'll notice here this is not balanced. We don't have any hydrogens, we don't have any waters here. So that is a problem, so we have to actually use this new method that I'm about to teach you. We'll do a lot of examples with these in class, so if you don't catch on to it in this video, don't worry. Okay, here guys, I know it's a little cut off at the top, but this is the way to balance two different half reactions, an oxidation half reaction and a reduction half reaction, and then combining them to balance an overall redox reaction in acidic solution. So these are rules, and we are going to do an example. Okay, so you have several different steps that you need to do. So we have that same copper. Okay, so step one is just to write the half reaction. So this is the reduction half reaction for nitrate. You have your nitrate, and it is going to be reduced, so it is gaining electrons here. All right, you write it all except for the for the waters, the hydrogens. So then what you're going to do in step two is balance all of the atoms except for oxygen and hydrogen, and you'll notice here nitrogen is already balanced. So step three is to balance the oxygen by adding H2O molecules. Okay, so you add as many waters as you need to make the O's balance on either side. So for this, you need to add 2 waters, and you actually add molecules to whichever side has less oxygens. That way you're going to balance it out. So here, we're adding 2 oxygen molecules to this product side in order to balance it out. So here now we have 3 oxygens to this 3 oxygens here. Okay, so step 4 is to balance the hydrogens. Okay, so to balance the hydrogens, we need to add our H+ ions. Okay, so here we have balancing our H+ ions. So we have 4 hydrogens over here, so we add 4 hydrogen ions right here. And then step 5 is to balance the charge by adding electrons. So we add electrons to whichever side we need to. So here we have -1 and a +4. So if we have 1 positive charge for every positive ion, so we have a +4 and a -1 here, so we need to have these 3 electrons here to balance this out, because otherwise with these by themselves what we have is a +3, so we need to add a -3, and that's going to balance out our electrons here. Okay. The next thing you need to do is the exact same thing with the oxidation half reaction. So you just write the reaction down in step 1, balance all the atoms except for the oxygen and hydrogen. Balance the oxygen by adding water molecules to the side with the least amount of oxygens. Balance for hydrogen by adding hydrogen ions. Balance the charge by adding electrons. Again. Again, if things are looking a little fishy and difficult, we are going to do a lot of practice problems in class. This is one thing that you need to pause this video and you've got to memorize these. These substances, nitrate, permanganate, and dichromate, they all want to gain electrons. They contain atoms which are higher or more positive oxidation states than usual. So when they gain electrons, the oxidation numbers of the atoms are going to drop to more appropriate levels. These are things that you just have to memorize. Just as a quick thing, in this particular one, nitrate has a +5 and it is going to drop to a +2 here. Okay, in permanganate, manganese has a +7 oxidation number and it drops to a +2. And here chromate has a +6 which drops to a +3. All of these are very high and they drop to more appropriate oxidation levels. Oxidation numbers. These have to be memorized. I would suggest doing some note cards to get these down. All right, substances with lower or less positive oxidation states than usual is something like in C2O4, carbon has oxidation states of +3. This is oxalate, okay, and it is going from what you see here as a +3, okay, and it is going to a +4. It is going to oxidize or lose electrons in order to raise its oxidation state. Okay. Next, we also have some nonmetals that can actually raise their oxidation states by bonding with like elements. So chlorine is going to, like hydrochloric acid. In hydrochloric acid, it can combine with a species that is easily reduced. So the chlorine ion is actually going to go from a 1 to a 0. And that's why we use sulfuric acid rather than HCl or hydrochloric acid to acidify solutions when we do redox titrations. We are going to do that in our next video. We'll talk about redox titrations, and hopefully that'll be what we do for our lab. If you ever have a choice between two species that can be oxidized, so you have compounds and they have things in the P block or the D block, metals, nonmetals, okay, and you have things like we just looked at, like that oxalate or that chlorine and hydrochloric acid, and they have less positive than usual oxidation numbers, the metal will always be oxidized. Right, I'm going to go over one more thing fairly quickly. We will do examples with all of this in class. I know this is a lot. So basic solutions, they actually have high concentrations of hydroxide ions. Okay, so permanganate, it goes from a +7 to a +4. Really? There we go. It goes from a +7 oxidation number to a +4 oxidation number. This is a common reduction in a basic solution. It is going to oxidize P or D block metals, sulfide ions, and substances that have lower or less positive oxidation states than usual. That happens in basic solutions. So basic solutions, like I said before, are the ones that have our hydroxide ions in them. And we are going to do a lot of practices with these half-reaction balancing method. So don't worry, I just want you to get this content in before we get to class.